Okay, so it looks like it's about time for us to get started. Probably I'll start with talking about, we've got another quiz coming up on Friday. This is the sheet I've got posted on Brightspace under test resources. Oh my goodness, cut and paste. I called it test 2, of course it's test 3. So Friday, it'll be a repeat of what we did last time. We'll start sharply at noon. I'll give you 23 minutes. Material covered 6, 7, and 8, so Monday, Friday, Wednesday. And then the list of equations I've got printed on the sheet are these right here. So that's up on Brightspace, ready for you to go through. I've got office hours this afternoon, so by all means drop by this afternoon. Thursday I'm a little busier, but if the door is open, you're welcome to come in. And then Friday morning I'm reasonably free, so you could get me in as well. Also by email if you have any questions. Lots of this stuff you can also ask at the Help Center, so if you're stuck and you can't find me, then you can absolutely drop into the Help Center and ask questions as you're getting ready. I've got your test 2s here if you want to grab them after class. I'm free to stick around for a few minutes afterwards and give them back and answer any questions you might have. The other thing I wanted to mention before we start is the problem sessions for next week. So people who did first year physics classes with us here are maybe familiar with the idea of problem sessions. They're going to run a little differently from first year because we're not first year anymore. So basically you go to your lab period at your lab time in the lab room. So you go just like you would go to a lab. When you get there, there's going to be a sheet of problems. And they cover the range of material that we've done up to about now. They're kind of building on things we've done in class before. The intent is to get you working, comfortable with going back and forth with your notes, trying new problems, reading it in new ways, and doing it. You'll work on the problems. The lab staff and the TAs will be there for sure. Me, well, Monday could bring a strike. I don't know what's going to happen to me. So strike or no strike, the problem session is going ahead. If there's a strike, you won't see me. If there's not a strike, I'll be there as well. So you'll work on those problems. You can have all the help you want. You can work with your classmates. You can work with your notes. You can ask questions of the lab staff and the TAs. If they get a bunch of questions coming up over and over, they might do some of the work on the board. The overall goal is for you to be able to read those questions, know what the question is, and be able to give a complete answer. So that's the goal. When you're done with those questions, you'll just staple it and pass it in at the end. I'll probably mark one of the questions just to go through and see how you did with it. So certainly it's to your advantage to make sure you're calling the help over and ask, am I on track? Is this part right? Do I have the right idea here? So please do take advantage of all that help. Yep.
Can you use your notes?
Yes, all your notes, calculators, whatever. The only thing I don't want you to do, don't take pictures of the problem session and upload it to CHAG. I will be very mad and pursue academic dishonesty charges. Right? So you're not allowed to post them online, but all of the resources totally fair. Yeah, and if you have no clue how to do one of the problems, call somebody over and say, look, I just have no way to know how to start this. Please get me going. They'll get you going, either open the notes to the right spot or give you the starting equations, tell you how to begin it. It's absolutely fine to not know how to solve a problem, but just please ask for help and they'll walk you right through it.
About how many questions is it?
I think I've got 4 questions written in total. I went through and made up the solutions for them. It's hard for me to say exactly how long it took me because I was sort of doing it off and on when I had free minutes. Yeah. I know it's a 3-hour period and I know you're all busy, so maybe you won't finish all 4 in the period, although maybe you should really try to. I'm going to ask that everybody gets at least the first 2 done and submitted.
Okay.
Yeah. So if you don't get to all 4, so be it. They're good for study come final exam, but make sure you get the first 2 done and passed in. I think that's totally doable for a 3-hour period with help. And I would encourage you to kind of work together with friends. And if you want to hop to different lab sections, that's probably cool with the lab instructors. Just ask them first so they know who to expect to what day. Okay, so I think that's everything I wanted to say before class. I'm going to post this with the lecture slides along with it being up on our test resources as well. So last day we did lots and lots about electric potential. We spent most of our times looking at equipotential lines. We got started on an example, but we did not get finished. So that's what we'll try and finish here today. And then we'll be able to get started on capacitors. So the example we started was we knew the electric potential in a region of space was given by this expression where we didn't know what A was. The first question was derive an expression for the electric field. So we knew we had to do the components by finding the derivatives with respect to x, y, and z. That gave us an equation for the electric field. Then the next thing we wanted to find was what was the value of that constant A. So we knew what the work done was, and we were asked to find A. We remembered that work was the change in potential energy, the negative of it, minus Q delta V. We knew the positions for our VF and our VI, so we were able to write those down, put in our work, and we solved for our A. Then we wanted to find the electric field at a certain point. We put in our numbers and found our electric field. Now we're moving on to part D, which reads a little bit funny, but it does ultimately, hopefully, make sense. So show that in every plane parallel to the XZ plane, the equipotential contours or equipotential lines are circles. So the first bit to decipher, what does it mean every plane parallel to the XZ plane? So X and Z are sort of horizontal like this. This is X and Z, and Y is up and down. So an XZ plane is just a plane that's horizontal relative to the ground, basically. So the palm of my hand. So X and Z are this way, Y is this way. The XZ plane are these two. So something that looks like this. Here's my attempt at a 3D drawing of this. So this would be a plane parallel to XZ. And we notice for this plane, I drew this one right at the origin. So for this plane, Y is equal to 0. So this plane is parallel to XZ. But this one up here would be as well, right? So if I moved it up in space, as long as Y was constant, we're still parallel to the XZ plane. So another plane, I guess I didn't need that sheet of paper. And we'll stay generic here. Another plane can be somewhere on the Y-axis as long as Y is constant. So I just lifted that plane up a little bit. So here's a plane parallel to XZ. So Y equals constant. Gives us a plane parallel to XZ. So now we know what plane we're talking about. The next part says, show that the equipotential lines, so the lines along which the potential is constant, show that they have to be circles. So if we wanted those lines to be a circle, why don't we see if we can figure out what that means? I'll start by drawing a circle in that plane. So a circle in this plane would look something like this, right? So we're saying show that the equipotential lines look like a circle like that. Well, if it's a circle, it has a radius r. So EPL equals a circle. What do we know about a circle? It has a radius. To find the radius, we would do the x squared plus the z squared. And of course, that would be constant. Okay, everybody okay with the idea? Okay, so a circle has a constant radius. And then the other bit we know is that y is also constant. So x squared plus z squared is constant, and y is a constant, and we're talking about equipotential lines. So let's write down our equation for our potential. So our potential equals V equals A times x squared minus 3A times y squared plus A times z squared. squared. So that's our equation for our potential. I could put in my value for A, but I just don't want to write all those numbers down. So what I'm trying to show is x squared plus z squared a constant? If it's a constant, then I know that this is true. If it's not a constant, then this isn't true. So is it a constant? So what is x squared plus z squared? Is it constant? So the first thing I'll do on this equation is divide both sides by a, so that v divided by a equals x squared minus 3 times y squared plus z squared. This is kind of looking like something. If I bring my 3y squared to the other side, and on the right I've only got x squared plus z squared. So if I look at this expression, V, I'm talking about an equipotential line, so V is a constant. I'm in a plane parallel to xz, so my y is a constant. So therefore, I see that x squared plus z squared is a constant. So it's true that my equipotential lines are circles. And the radius of those circles is v over a plus 3y squared. Okay, so I think part D was almost more an exercise in reading the problem, deciphering the different bits and pieces, than doing any kind of difficult math. And sometimes problems are going to be more like that. Okay, then part E, what is the radius? So find R. If our potential is 1280 volts, and we're at a height of 2 meters on the y-axis. So for part E, V equals 1280 volts, y equals 2 meters. X squared plus z squared is the radius r squared equals v over a plus 3 times y squared. So then my radius is the square root of v over a, 1280. A was 640. Plus 3 times y squared, so 3 times 2 squared. That gives us a radius of 3.74 meters. I think it's kind of neat that the radius depends on y, so that radius gets bigger and bigger the further up you go. So it's kind of interesting. If this were like a computer modeling course, you'd probably write a program to draw those equipotential surfaces. If you're into modeling, you might like to try that. I'm not sure I could do that anymore. It's been a long time since I did that sort of thing. Okay, any questions? Okay. So that leaves us ready to start chapter 24. We're going to stay with that material for quite a while. So chapter 24 is all about capacitance and dielectrics. Capacitors, maybe you remember from physics 10 and 51, we also discussed it a little bit when we did our electric fields chapters. We've got two plates, they have an area, they have an amount of charge, equal and opposite charge separated by a small distance. That's a capacitor. Capacitors are circuit devices. Mostly we use them to store energy, so all of your electronics are full of capacitors. And all of these pictures here are kind of pictures where capacitors are important. So touch screens all work because they're capacitors. There's electronic circuits inside. You bring your finger close to the surface. Your finger is full of electric fields. So that electric field changes what's happening with your screen and it recognizes where you touch it, because it can sense that electric field. Keyboards are little capacitors. There's a capacitor under every key so that when you touch it, it knows which one you touch. And then those right there, those are some typical capacitors that you might see in some circuitry. So we're going to do a little bit of a quick recap, what we know about capacitors, and then we're going to get right into dielectrics, and then we'll start talking about energy and circuits. So our definition of the capacitor, two conducting plates, each with area A. They're separated by a distance d. So the distance between the two plates is generally given by a lowercase d. The plates always have equal and opposite charge. So one plate is positive, one plate is negative. That charge separation leads to an electric field between the two plates. So these lines are the electric field lines. Typically, this distance here is very small compared to the linear dimension of the plates itself. So typically D is, we'll just say very small. And the reason we keep D very small is that makes this close to what we would call an ideal capacitor. In an ideal capacitor, these electric field lines would go straight across and they'd be parallel everywhere. Those are the kind of lines we've drawn in all of our problems so far. In real capacitors, you get this little bit of bending of the fields at the edges. That's called fringing. But if we can keep D really small and A pretty big, then you don't get much of those real effects and your capacitors work better. So D is very small. And then we'll say that's to keep the electric field uniform. What else about capacitors? Everything we've done so far says that the space between the capacitor plates is empty. So the space may be empty. When the space is empty, the electric field between the plates is the charge density divided by epsilon naught, where epsilon naught, as the reminder, that's the permittivity of free space. Equals 8.85 times 10 to the minus 12 coulombs squared over newtons times meters. And what the permittivity of free space more or less means it's how electric fields can move through a vacuum or through air. So that's what that parameter tells us about. Right off the bat, you might recognize a problem with actually trying to fabricate a capacitor. You have these two little tiny plates and you want them close together. If the two plates touch, all of a sudden you've got a short circuit and you can't get that electric field because there's no distance between them anymore. That's a problem in your circuit, so you don't want the plates to touch. The way we make that happen is we put something between the plates, and that something is called a dielectric. So the space between the plates could be empty, or we could fill it with a dielectric. So that would be a material that fills up all the space between the plates, or filled with a dielectric. If we fill it with a dielectric, our electric field is sigma over what we call epsilon. And that would be the permittivity of the material, and it tells us how the electric field can go through that material, right? Instead of how it goes through a vacuum, how it goes through the material. Okay, so far so good? We're going to spend a fair amount of time talking about this dielectric stuff, how that works and what it does to the field and the capacitance and the charge and all that stuff. So our capacitors are circuit devices, so we're going to want to draw circuit diagrams and think about how we use them in circuits. So the first thing we'll do is let's go from our real picture of a battery connected by wires to a capacitor and show what that looks like in a circuit diagram. So for our battery, we represent that as a long line and a short line. The long line is the positive, the short line is the negative. Then we take our battery, we say that that has a potential. Pretty often we call it an epsilon for potential, that's really common. So epsilon. The other one you might see would be delta V, sometimes with a subscript like DAT for battery. So either epsilon or delta V, that means the potential of that source. Then we connect it to some ideal wires. Ideal wires are just straight lines, so either the top and bottom. So these are ideal wires. Ideal wires mean they have no resistance at all. That can't be perfectly true. Usually the resistance is really small, so it's close enough to true. So we're kind of okay with those. Our capacitor in the circuit is represented by just two longish parallel lines. So there's our capacitor right here. We'll label that C for capacitor. All good there? So then what happens in our circuit is as soon as we connect that, inside the battery, there's a chemical reaction. And that chemical reaction makes a positive charge flow towards the top terminal of the battery. When the positive charge gets to the top terminal of the battery, it touches this conducting wire. It's allowed to flow, so it comes along the wire down here, and then it hits that capacitor plate. We know, of course, now at this point that this is not actually what happens. We know what actually happens, that it's the negative charge that flows around. However, the people, when they first started thinking about these things, they didn't have the knowledge that it was a negative charge that moves. They thought it was a positive charge that moved. So they labeled it the positive. All the books have been written that way ever since, so I go along with those books. But we do know now that in actuality it's the negative charges that move. But for historical reasons, we talk about moving positive charges. Okay, so our positive charge is flowing around the circuit, flowing around this wire. That's what we call current. So the positive charge leaves the battery, comes up here, around, hits this top plate. When it gets to the top plate, it's no longer in contact with anything, so it can't go anywhere. It has to stay on the top plate. This bottom plate is also full of charges which are allowed to move. So when a positive charge hits this top plate, it repels a positive charge from this bottom plate because it feels a repulsive force. So a positive charge leaves that plate and goes away. If we're down a positive charge, then overall we're left with a negative charge. The bottom plate becomes negative. And then that repeats until the plates are full, until they have the maximum amount of charge. So that just goes over and over and over. When the capacitor is full, so when it gets the maximum amount of charge it can hold, we know that the potential of the battery, which we might call epsilon, is going to be equal to the potential of the capacitor. When those two things are at the same potential, no more charge is going to flow, and that's how we know it's completely full. So the potential of the battery limits how much charge can get stored on those plates. If we want to store more or less charge, we will put a battery with more or less potential. Okay? So the battery limits how much charge. This kind of a circuit, where we hook it up, current flows for a while as it's charging, and then it stops. Those are useful in circuits where you want current only to flow for a short time. And an example might be intermittent wipers on your car. So you want them to come off and turn off, right? You want them to come on, turn off, come on, turn off. That's this kind of a circuit. Okay? All right. Good to there. So let's talk about what's going on inside the capacitor a little bit more. We see on this picture that one plate is positive, one plate is negative. We know there's a potential difference across the plates, so we know there's an electric field here, so we want to introduce some ideas about the electric field to tell us about the capacitor. So there's our picture again. Right here I've just got a two-dimensional picture of a capacitor because that's just easier to draw. So the first thing we say is that we characterize a capacitor by its capacitance. So a battery has voltage or potential, a resistor has resistance, a capacitor has capacitance. Okay, so that's what we use there for capacitance. That has a symbol of C, something to be careful of. Don't confuse your C for capacitance with your C for coulombs of charge. I know that's just a small thing, but it's easy sometimes to get tangled up. Just make sure you know which C is which. So as we charge up our capacitor, one plate becomes positive, one plate becomes negative until it's fully charged. Because one plate is positive, one plate is negative, we get an electric field that goes from the positive to the negative. Okay, so a lot of this here is review. The separation between the plates, we said that that plate separation was D. One charge, one plate is positive, one is negative. So one plate would have a positive charge density, one would have a negative. We'll notice that the net charge on the plate is plus Q to minus Q, net charge on the capacitor. So the total charge is 0, but it is separated. That's what makes the electric field, is that separation of charge. So let's write down what we know about electric field and electric potential. We know that the field between the plates is sigma over epsilon naught, assuming there's nothing between the plates, so no dielectrics yet. And we also know that the potential difference between the plates is the electric field times the plate separation. So we're going to put those two things together and we're going to come up with something for our capacitance. So let's start with potential is field times distance. Let's put in that our field is sigma over epsilon naught. And then we'll remember that sigma is our charge density. That's charge divided by area. So then what we see here, that our potential is charge times distance divided by area times epsilon naught, or our charge, solve for Q, is A times epsilon naught divided by distance times the potential. This expression shows us that the net charge on the plates is proportional to the potential difference across the plates, okay, which is what we talked about when we said about how we charge up the capacitors. The amount of charge you can store depends on the potential of the battery. So if it's proportional, it has a constant of proportionality, and that constant of proportionality is what we call the capacitance. Equals capacitance. Capacitance has our symbol of C, so our capacitance is A times epsilon naught over D. And our capacitance is the charge on the plates divided by the potential between the plates. Okay, so there's two ways to find capacitance. Some things to notice here. I think this is real interesting. The capacitance itself, it only depends on the physical parameters of the plates. How big are they? How far apart are they? And what's in between them? So the capacitance only depends on the plates themselves, so that's kind of interesting. Let's go for the units of capacitance. So the units are called farads after Michael Faraday. That has a symbol of a capital F. And a farad is a coulomb divided by a volt, or coulombs squared over joules. If you think about the units of capacitance, and we kind of get to the joules here because we know that potential is charge times voltage, coulombs times volts. If you think about the fact that joules are hidden in the units for capacitance, it tells us that capacitance is a measure of energy. And it turns out it's a measure of a device's ability to store energy. So capacitance tells us how much capacity does it have to store energy. Okay, I think that's everything for this slide. Any questions? Okay, we'll keep going. Why don't we just pause and take a moment to sort of look at capacitance on one of those FET simulations. So if you Google FET PHET capacitors, it would take you to this simulation. So what I have here, these two plates are the capacitors. I'm going to click off the box that shows me the top plate charge, click off the box that shows the electric field. If I take my capacitor and I hook it up to the battery, right now it's on 0 volts. If I bring it up, see as I increase my potential, I'm getting an electric field between the plates and I'm getting charge stored. Something I think is interesting here, as I change my potential, the capacitance doesn't change, that stays the same. The electric field, and the charge on the plates, that all changes, but the capacitance itself does not change. So that's kind of an interesting result. So I'll set it at 1.5 volts. Let's see what happens if I change the area of the plates. If I make the area smaller, we can look at what happens to the capacitance. So a smaller area, making the plate separation smaller. As I bring the plates closer together, I get more capacitance. And if I make the area of my plates smaller, if it has a smaller area, we have a smaller capacitance. Okay, so this is not a very fun simulation, but it does show those effects. I picked the two simplest examples I could think of to make a homework question. So use the equation for capacitance to find the capacitance here, you know, the charge and the potential. And then I talked about those units of capacitance. Here I'm asking you to show that it's equal to coulomb squared per joules. So I will post the answers to those with the class notes. And now we'll do a different example. So a parallel plate capacitor has a capacitance of 1 farad. The plates are 1 millimeter apart. What's the area of the plates? So our capacitance is 1 farad. The plate separation is 1 millimeter, or 1 times 10 to the minus 3 meters. And I would say that this is not an atypical separation. Certainly that could happen in a capacitor. Lots of times it's going to be smaller, but you know, this is certainly possible. So our capacitance C is epsilon naught times the area of the plates divided by D. We're trying to find the area. So that's going to be the plate separation times the capacitance divided by epsilon naught. So we've got 1 times 10 to the minus 3 meters times my capacitance of 1 farad divided by epsilon naught, because there's nothing in between the plates. Alternate units for epsilon naught are farads over meters, 1.13 times 10 to the 8 meters squared. Okay, let's take stock of our answer. Does that feel right? If these were square plates, these plates would be about 10.6 kilometers by 10.6 kilometers. Feel reasonable? Got that stuck inside your calculator or your cell phone? I don't think that's reasonable. Okay, so one of the things this example is showing us is that 1 farad is a ridiculously large capacitors. Most of the capacitances that we'll come across, that you'll see in devices and we'll deal with in this course, will be kind of on the scale of microfarads to picofarads. So 1 farad is big. Typically, we'll work from microfarads to picofarads. And you should get comfortable with these units and know what they stand for. So a micro is 10 to the minus 6, and pico is 10 to the minus 12. Also, we'll use nanofarads, which is 10 to the minus 9 farads. So you should remember all those prefixes as best you can. Overall in our devices, we do want to have high capacitances. So the bigger the better, because if we have a big capacitance, we can store lots of energy. But we do have to be careful, because if the electric field between the plates gets too big, the same thing happens with a capacitor that happens when I brought in the Van de Graaff last time. If your electric field gets bigger than 3 million volts per meter, it's going to spark between them. You're going to get a dielectric breakdown. So you get a spark between the plates. Your device will catch on fire, right? So we have to be careful. So we want our capacitances high, but we don't want the electric field so high. So when we think about our capacitance, which is epsilon naught times A over D, let's think about each of those parameters and what we can do with them. So the first one is this epsilon naught, or permittivity of free space. One way we can change the capacitance is to change this, and you change this by putting a dielectric between the plates. Putting the dielectric between the plates introduces an advantage to this D, because you can make D smaller. So my very simple demo I have is 2 sheets of tin foil. So 2 sheets of foil, if I charge them and I hold them a small distance apart, they're now a capacitor, right? If I try and get them close, it gets a little bit tricky because the foil can touch each other. If you have a dielectric, which can be a little piece of plastic, that's really thin, I can put it between the 2 pieces of foil and they no longer touch. Okay, so that's a way to make your D really small. If you wanted to put this in your cell phone, it would be difficult because it's bigger than your phone. So something you can do to deal with that area is you can just insulate the outside of the plates as well and roll them up. So this would be people who are maybe interested in how you make things like this, which is definitely the kind of person I am. You roll them up, and all of a sudden you get a smaller device which fits inside stuff. That's why the capacitors you see inside circuits, probably the ones you use in the lab, that's why they're all round, right? So it's 2 metallic sheets, a dielectric between them, and it's all rolled up. It gives you a bigger area for a physically smaller device. So we're going to work on this equation a little bit and start talking about dielectrics. So our definition of a dielectric, it's an insulating material placed between the plates of a capacitor. So that's what a dielectric is. It's just an insulator between the plates. Of course, it needs to be an insulator so it doesn't short out the device. If it was a conductor, the current would just flow on through. So it does have to be an insulator. And it serves 3 purposes. It keeps the metal plates from touching each other, so it prevents short circuits. It increases the maximum possible potential between the plates. This one, we sort of figured this out experimentally, and then we can show it's true using the theory we can talk about. And then it also increases the capacitance compared to a capacitor with no dielectric. So we're going to go through these and see how they work. So to start thinking about this stuff, let's first look at the capacitor without the dielectric, if it just has empty space between the plates. So we're going to take our two plates, no capacitor between them, we're going to connect it to a battery, and the battery is going to have a potential delta V, and we're going to write down the things that happen. So our first step is connect capacitor to a battery with potential delta V0. So then the process that we outlined in that circuit diagram, the charges lie the flow and so on until the capacitor gets fully charged. The charges go on the two plates, gets fully separated. We've got the electric field happening between the plates. So we can draw our electric field between those plates once it's fully charged. Okay, it looks something like that. There's our electric field E. So what we know about our capacitor, when it's fully charged, so it's holding the maximum charge possible, the charge on the plates is plus or minus Q0. One plate is positive, one plate is negative. And we'll say 0 to mean we're talking about a capacitor with nothing between the plates. The charge density would be the charge divided by the area. One of those is going to be positive, one of those is going to be negative. We'll put an O on it to mean we're talking about no dielectric. The potential between the plates is the same as the potential of the battery, delta VO. And then the capacitance of this capacitor is CO equal to QO divided by the potential, delta VO. Okay, so this is everything we had for that original capacitor that we hooked up to a battery. Next, what we're going to do is two things. We're going to remove the battery. After we remove the battery, we're going to put a dielectric between the plates. Okay, and those steps are important. If you did it the opposite way around, we get a different thing happening. So we take the battery out first, then we put the dielectric in. Because we've removed the battery, no more charge can flow. This is not connected to a circuit anymore. So the battery is gone, the charge has to stay the same because it can't go anywhere. So with the dielectric, the charge stays exactly the same because it can't flow. So no change there. Charge density also doesn't change. The potential, and this is something we definitely see experimentally. So when we do this, we hook it up to a voltmeter. We see that the potential of the capacitor with the dielectric, delta VC, actually drops. So that's definitely true because we see it. And then the capacitance is C equals the charge, QO, divided by the potential, delta VC. So the capacitance changes. So we pop in the dielectric, we get a different capacitance. Let's compare this capacitance to this capacitance and see what we get. So this new capacitance, C, is QO over delta V times C. QO from this equation, QO equals CO times delta VO. So we'll put that in right here. And I'll just put in some brackets. So our new capacitance is related to the old capacitance by this ratio of the potentials. Because the potential drops, this thing is bigger than 1, our new capacitance is bigger. And this one is bigger. Our capacitance increases. Okay, questions? And so far, we're seeing this is true because of an experimental result, because we know that the potential drops. Okay, so we see this to be experimentally true. We pop in that dielectric, we get a bigger capacitance. So there's our experimental results. Now let's use all of the ideas, what we know about the electric field, and let's see if we can explain it with the things that we know. So why did that potential drop? So on this slide, I pretty much just put in a recap of our previous slide, so we would have that next to us as we're working. And then here is a 2D picture of my capacitor, because I'm going to find this one easier to draw on than my 3D version. So recap what we know about our capacitor without the dielectric. If there's no dielectric, we get an electric field between the plates. From the positive to the negative, looks like this. And if over here is our 2D version, I can draw it over here as well, from here to here. So without the capacitor, I get an electric field that I'm now going to call E with a 0 on it, so 0 for no capacitor. That's sigma over epsilon naught, and we know it points positive to negative. That E0 is on this picture as well. Okay, so we hook it up, we connect it to a battery, we've got a potential difference, we've got a charge separation, we get the electric field. We're pretty comfortable with that idea right now. When we put the dielectric between the plates, we still have that separation of charge, so we still have that electric field, right? So the electric field doesn't turn off just because we have the dielectric. So if we place the dielectric, we still get that original field. So in our new picture, our 2D picture, we place the dielectric. Here it is right here. Here's our dielectric. And that original field did not go away. That's still there. So far, so good? Okay, what's the effect of that electric field? So I've got a material sitting in an electric field. My material is full of molecules. Some molecules are definitely free to move around a little bit. So molecules, in general, will have an end that's a little more positive and a little more negative. Most materials, it's all randomly sorted, and they're all kind of lined up randomly. If you take that material, you put it in an electric field, the molecules are going to start to flip. So they're going to start to turn around like this. Where the plus ends are going to get pushed with the electric field. And the negative ends will get pushed against the electric field. Okay, so the molecules inside the dielectric will start to polarize. So as they start to line up, we say that that's making them polarized. If those molecules are flipping, then one end of the dielectric is a little more positive, and one end is a little more negative. Not loads, but a little more. If one end is a little positive, one end is a little negative, that means we get a new electric field inside the dielectric. It will induce an electric field, EI for E induced. Okay, oh, and that takes us right to time's up. So what we'll start with, we'll finish up on Friday, is thinking about that net electric field, what happens when we add the two of them together. So we'll start Friday with our quiz, and then we'll finish up this material.